Good morning to all. I am Arul Jothi, working as Assistant Professor in the Department of Computer Science, Fatima College, Madurai. Today we are going to discuss some algorithms in cryptography. So cryptography is used to encrypt data that is in readable format into an unreadable format. For this, we use two types of algorithm. One is symmetric algorithm and another one is asymmetric algorithms. In symmetric, we use same key both for encryption and decryption, whereas in asymmetric encryption, we use two different types of key. One is public key and another one is private key. So in symmetric encryption, we have different types of algorithm. Start with AES, and now we are going to see in this session about AES algorithm, that is Advanced Encryption Standard. So in replacement of DES, here comes the AES to overcome the drawbacks of DES. So DES is followed by triple DES, which is 3 times we have to process DES algorithm to make the performance better. But beyond that limit, it has some drawbacks. To overcome the issues, research was going on, and Rinjaral was selected as the AES in October 2000. And it is issued as FIPS publication 197 standard in November 2001. So the AES, popularly known as Rinjaral algorithm, was designed by Richmond Damon in Belgium. It has 3 types of input bit keys, that is 128, 192 and 256. So 128-bit data, an iterative rather than feastal cipher, processes data as block of 4 columns of 4 bytes, operates on entire data block in every round. It is designed in such a way that it goes on 5 steps. So this is the diagram showing the AES encryption process, starting with the plain text and then the 16 rounds it goes on. And next we are going to see the AES structure. In AES structure, we discuss about the data block of 4 columns of 4 bytes, in the key expansion and substitution box, shift rows, mix columns, add round key, and in the XORing operation as an alternative. So initial XOR key with fast XOR and table lookup implementation. So these are the main 5 processes we are going to undergo in AES structure. That is add a round key, substitution bytes, shift rows, mix columns, and again we are going to add round key. So mainly we are going to see 4 processes: add round key, substitution bytes, shift rows, and then mix columns. So we have some basic commands on this AES. It is a fast feastal cipher. It is a key expanded into array of 32-bit words. It has 4 different stages as shown in the previous slide. Only add around key uses it as a form of Vernam cipher, and each stage is reversible. So decryption is easy in reverse order. So first one is substitution bytes. How we are going to perform this phase? A simple substitution of each byte uses one table of 16 into 16 bytes containing a permutation of all 256 8-bit values. Each byte of state is replaced by byte indexed by row left 4 bits and column right 4 bits. For example, byte 95 is replaced by a byte in row 9, column 5, which has value as 2a. So S-box constructed using transformation of values in GF to power 8. It is designed in such a way it is resistant to all known attacks. So this is an image showing the substitution box, and this is an example that shows the substitution bytes. Next one is shift rows. A circular byte shift in each row. First row is unchanged. Second row does 1 byte circular shift to left, and third row does 2 byte circular shift to left, and the fourth row does 3 byte circular shift to left. Whatever we perform in encryption, that is shift left, we have to perform shift right in decryption. So decryption inverts using shifts to right. So since state is processed by columns, this step permutes bytes between the columns. And this is an example showing the shift rows. This is the structure and this is an example. Next, mixed columns. Each column is processed separately. Each byte is replaced by a value dependent on all 4 bytes in the column. Effectively, a matrix multiplication in GF2 power 8 using prime polynomial is used in this mixed columns. So this is again an image showing matrix multiplication performing mixed columns. And this is the example that how we perform this mixed columns by multiplying the matrices. In AES arithmetic, uses arithmetic in the finite field GF2 power 8 as already we discussed with irreducible polynomial, which is this is an example showing how the matrix multiplication is performed for mixed columns. So 02 is multiplied with 87 mod 11b. This is an example and our output is this. So this way the operation is performed. Next, about again some concepts in mixed columns. We can express each column as 4 equations to derive each new byte in column. Decryption requires use of inverse matrix with larger coefficients, hence a little harder. Have an alternate characterization and each column a 4-term polynomial. Coefficients based on linear code with maximal distance between code words. And add round key. XOR state with 128 bits of the round key again processed by column, though effectively a series of byte operations. Inverse for decryption identical since XOR own inverse with reversed keys. So designed to be as simple as possible, it is similar to Venom cipher, but it maintains complexity and security. And again, this is an example of add round key. And these are the steps that we go in AES round. So AES key expansion. It takes 128 bit, that is 16 byte key, and expands into an array of 44, 52 or 60, that is 32 bit words. So start by copying key into first 4 words, then loop creating words that depend on values in previous and 4 values places back. In 3 or 4 cases, just XOR these together. So first word in 4 has to rotate plus the substitution box plus the XOR operation and constant on previous before XOR 4th back. So this is the step we go through this in AES key expansion. Okay. Next, key expansion rationally designed in such a way that it resists known attacks. Its design criteria include knowing part key insufficient. If we know the partial key, we cannot detect the key. And invertible transformation. Fast on wide range of CPUs. Use round constants to break symmetry. Diffuse key bits into round keys. Enough non-linearity to hinder analysis. And it's so simple of description. So these are some examples for key expansion in EAS. So here we discuss about an avalanche effect. So avalanche effect is nothing but if it is make a small change in the key, a single bit, the output is collapsed. The ciphertext is totally changed. This is known as avalanche effect. This is maintained in AES algorithm. So in AES decryption, it is not identical to encryption. We have to perform all the process in reverse one, but can define an equivalent inverse cipher with steps as for encryption. Works since result is unchanged when swap byte substitution and shift rows, swap mixed columns, and add round key. So with the help of this mixed columns, swap bytes and shift rows and all these XORing operations, the security of AES algorithm is maintained. So in the reverse process for decryption, we have to perform all the inverse processes. So its implementation is, in implementation point of view, it is very simple but unsecured. So on the whole, AES algorithm is the best symmetric encryption algorithm. Thank you, girls.